In the heart of summer, 1943, German technical staff gathered at the Kummersdorf Proving Ground, an installation 25 kilometers south of Berlin. Before them sat an American tank, recently captured from the Tunisian desert, its form bearing the indelible marks of 4 months of relentless fighting. Desert dust still caked its tracks. The North African sun had scorched its paint, and small arms fire had left numerous dents across its hull. Yet, when a technician climbed into the driver's position and engaged the starter, the engine responded immediately. The large radial continental power unit sputtered once, then settled into a steady, deep thrum. A quiet, knowing exchange of glances passed among the German specialists. Their own formidable Panther and Tiger designs routinely suffered disabling mechanical failures during simple transit marches to the front lines. Gearboxes seized, final drives stripped, and engines frequently overheated. This American machine, however, had endured over 5,000 miles of intense combat operations across North Africa and functioned with the surprising reliability of a newly assembled vehicle. The senior engineer present immediately ordered a complete dismantling. Every single component was to be meticulously examined, measured, and exhaustively documented. The insights gleaned from its internal structure would fundamentally contradict every prevailing German design philosophy regarding armored warfare. Meanwhile, 6,000 miles away, in a large factory situated just outside Detroit, workers on the night shift were already constructing another Sherman. They would complete this new unit in less than a day. By the time the German engineers compiled and submitted their official report, American factories would have produced an additional 1,000 such tanks. German military strategists firmly believed they possessed the world's most advanced armored fighting vehicles. The Americans were poised to demonstrate that the true measure of a tank's worth was not its ability to dominate isolated battles, but its unwavering capacity to consistently arrive on the battlefield and engage. This fundamental misjudgment stemmed from a deep divergence in engineering philosophies, traditions that stretched back decades before the current conflict. German engineering culture placed a premium on precision, intricate complexity, and theoretical perfection. The same national mindset that produced Mercedes-Benz automobiles and Zeiss optical systems applied these rigorous standards to the instruments of war. Each tank was conceived as a mechanical masterpiece, an integration of the most powerful available gun, the thickest possible armor, and the most sophisticated fire control mechanisms. The Tiger tank perfectly embodied this detailed approach. When it entered service in August of 1942, it represented the most potent armored vehicle then operating on any front. Weighing 57 tons, it mounted the devastating 88mm gun, adapted from a renowned anti-aircraft weapon, and carried frontal turret armor up to 100mm thick, with its gun mantlet reaching 120mm. In a direct confrontation, a Tiger could effectively neutralize any Allied tank at ranges exceeding 2,000 meters, while remaining almost impervious to return fire. The Panther, which saw its first combat deployment in July 1943, combined formidable offensive capability with significantly improved mobility. Its high-velocity 75mm gun could pierce 111mm of angled armor at 1,000 meters. Its sloped frontal armor, an adaptation inspired by the Soviet T-34 design, offered protection equivalent to much thicker vertical plates. German engineers largely considered it the finest medium tank design of the entire conflict. These powerful vehicles instilled profound dread among Allied tank crews. American tankers began referring to the Tiger simply as the monster. They frequently spoke of observing their own shells deflect harmlessly off its thick armor, while incoming German rounds tore through their Shermans as if they were made of paper. The sheer psychological burden of confronting German heavy tanks contributed significantly to a persistent mythology, one that endures to this day, that German armor was overwhelmingly superior to anything the Allied nations could field. German engineers, upon inspecting the Sherman, perceived a vehicle that violated nearly every principle they held sacred. The American tank weighed a mere 33 tons. Its 75mm gun, while adequate against older German types, such as the Panzer III and Panzer IV, struggled notably to penetrate the frontal armor of the newer Panthers and Tigers at typical engagement distances. Its armor protection, ranging from 50 to 76mm depending on the variant and production date, was demonstrably vulnerable to the standard German 75mm gun at combat ranges. Furthermore, its relatively high profile made it an easy target to spot on the battlefield. On paper, the Sherman appeared outclassed in every category that German metrics deemed significant. This initial assessment was not entirely unreasonable, given the specific criteria German engineers use for evaluating armored vehicles. German armor consistently achieved tactical victories against Allied forces throughout the war. A single Tiger, when commanded by a highly skilled crew, often managed to destroy multiple American tanks before finally being incapacitated. Kill ratios in individual engagements frequently favored German armor by margins of 3-1 or even higher. Michael Wittmann, arguably the most celebrated tank ace of the war, is credited with destroying over 130 enemy vehicles during his career, a significant number of them Shermans. However, the German analysis contained a fundamental, fatal flaw. They evaluated the Sherman solely by the criteria of tank versus tank combat effectiveness. They failed to measure it by the overarching standards of industrial warfare. They meticulously counted guns and armor thickness, yet they overlooked critical factors like available factory floor space and global shipping capacity. They calculated precise penetration values, but neglected to account for rapid replacement rates. The specific tank undergoing examination at Kummersdorf had been seized near Spitla, Tunisia, on February 22, 1943. It was identified as an M4A1 variant, distinguished by its cast hull, one of only 134 units manufactured by the Lima Locomotive Works in Ohio during July of 1942. Its United States Army registration number was 306-7641. A reconnaissance patrol from Schwer Panzerabteilung 501 had discovered it abandoned, yet largely intact amidst the disarray of the Kasserine Pass offensive. American forces had withdrawn so precipitously that they left significant amounts of equipment scattered across the desert. Recognizing the considerable intelligence value of an undamaged enemy tank, the Germans transported it 350 kilometers overland to Tunis, a journey that consumed 4.5 days over difficult terrain. From there, it was shipped directly to Germany, where it received the military registration WH-05894117 and the testing designation Versuchsfahrzeug number 259. The Kummersdorf facility itself had served as a weapons testing site for the German Army since 1875. Its engineers had evaluated Germany's earliest tank prototypes during the Great War, tested the initial panzer designs that would conquer France, and meticulously examined captured French, British, and Soviet equipment throughout the present conflict. They approached the Sherman with the same systematic thoroughness characteristic of German technical work. The process began with a static analysis. Engineers precisely measured every armor plate, stenciling its thickness in millimeters directly onto the hull with white paint. The vehicle was photographed from every conceivable angle, meticulously documenting damage and where patterns that offered clues about its operational history in combat. They noted the tracks showed substantial wear but remained fully functional. The engine compartment, while dusty, appeared well-maintained. The main gun displayed signs of extensive use, but no excessive bore erosion. Following this initial inspection, functional testing commenced. The Germans operated the Sherman across the Kummersdorf proving ground for several days, subjecting it to the identical trials used to evaluate their own vehicles. A kilometer-long hilly track tested its suspension performance and engine endurance. Cross-country courses assessed its mobility in challenging terrain. Speed trials measured its acceleration and maximum velocity. At every single stage, the Sherman performed consistently within its published specifications, despite thousands of miles of previous operational use. The subsequent ballistic tests, however, yielded results that largely confirmed German assumptions regarding the Sherman's inherent vulnerability. Utilizing armor plates of identical composition and thickness to the Sherman's hull and turret, German gunners determined the penetration ranges for their standard anti-tank weaponry. The 88mm gun of the Tiger could penetrate the Sherman's differential housing from 2,100 meters and its turret front from 1,800 meters. The Panther's high-velocity 75mm gun achieved comparable results. German gunners possessed the capability to destroy Shermans at distances where the American tank's own primary weapon posed little discernible threat. Yet, when the Germans subjected the Sherman's upper glacis plate to realistic combat conditions, simulating angled impacts, they uncovered something entirely unexpected. When the tank was positioned 30 degrees from perpendicular to the incoming fire, representing a vehicle not facing its attacker directly, the compound angle created by combining the glacis slope with this horizontal rotation resulted in an effective armor thickness exceeding 100 millimeters. Under these specific conditions, the Tiger's 88mm gun proved unable to penetrate this surface at any range. Even the Panther's superior main gun required the Sherman to be facing directly forward to achieve penetration of the upper hull. This particular finding did not fundamentally alter German tactical doctrine, as tank commanders were already instructed to maneuver for flanking shots against enemy side and rear armor, regardless of the specific vehicle encountered. The Sherman's side and rear armor remained highly vulnerable, and its turret could still be penetrated at typical engagement ranges. However, the unexpected result from the glacis test hinted at a design consideration the German engineers had not fully appreciated. American designers had clearly thought carefully about the practicalities of how tanks actually performed in combat, not merely how they appeared on specification sheets. The more significant revelations emerged as the engineers meticulously examined the Sherman's internal mechanical systems. Here, the profound differences between German and American design philosophies became starkly apparent. The first major surprise was the gyroscopic gun stabilizer. No German tank possessed anything comparable. The Westinghouse system employed a rapidly spinning gyroscope to detect the tank's vertical motion and automatically adjust the gun's elevation to compensate. The Euro rotor spun at over 12,000 revolutions per minute, providing a stable aiming reference regardless of the hull's movement over rough terrain. Electric motors connected to the gun mount responded to signals from the gyroscope, effectively keeping the barrel pointed at the same target in space, even as the tank pitched and rolled. A Sherman crew could engage targets while moving at 15 miles per hour with approximately 70% accuracy at ranges up to 300 yards. While accuracy decreased at longer distances, the fundamental ability to fire on the move still conferred a considerable advantage. German tanks, by contrast, were forced to halt completely to fire accurately. In the chaotic, dynamic environment of mobile warfare, the capacity to deliver fire while advancing provided a critical tactical edge. A Sherman could press forward under fire, engaging targets as it closed the distance, whereas a Panther or Tiger had to make a binary choice between firing and repositioning. German engineers meticulously photographed the stabilizer mechanism and documented its components with characteristic precision. They identified the gyroscope housing, the elevation motor, the control unit, and the power supply. They meticulously traced the electrical connections and measured the system's response times. The entire mechanism required only 24 volts of electrical power to operate. Yet, despite this comprehensive analysis, Germany never successfully fielded an operational tank gun stabilizer during the war. The immense engineering resources and manufacturing capacity required to develop and produce such complex systems at scale were continuously diverted to other, equally pressing priorities. The second profound surprise lay in the standardization of parts. The Sherman's designers had incorporated interchangeability into the vehicle's core design from its very inception, following principles American industry had refined over decades of mass production. Any suspension bogie from any of the 11 American production facilities could be unbolted and seamlessly fitted to any other Sherman. The same principle applied to road wheels, track links, drive sprockets, idler wheels, engines, transmissions, and virtually every other major component. This standardization extended beyond individual tanks to encompass the entire fleet. A Sherman constructed by Chrysler in Detroit utilized the exact same parts as one built by Fisher in Grand Blanc or Press Steel in Chicago or Lima Locomotive in Ohio. Supply officers could requisition replacement components without needing to specify which particular factory had originally built the vehicles they supported. Parts salvaged from irreparably damaged tanks could be used to repair other units, regardless of their origin. A supply depot in France could receive shipments from any American factory and distribute them to any American unit without concern for compatibility. The logistical implications of this approach were immense. Instead of tracking thousands of unique part numbers for each factory and production batch, American quartermasters managed a single, unified inventory. Instead of maintaining separate, complex supply chains for each manufacturer, they operated one streamlined system that served every vehicle and every unit. This simplification cascaded through every echelon of military organization, from the central depot to the division level and down to the individual tank crew. German tank production followed a starkly different paradigm. Each manufacturer produced components according to its own specifications, utilizing its distinct tooling and interpreting design drawings in unique ways. A transmission unit from one factory might not fit a tank produced by another without substantial modifications. Even within a single factory's production run, variations accumulated as designs were subtly modified and improved based on combat experience and ongoing engineering refinements. A Tiger built in January might necessitate different replacement parts than a Tiger produced in March. This fragmented approach created an escalating logistical nightmare, which only worsened as the war progressed and production was increasingly dispersed to mitigate the effects of Allied bombing raids. Spare parts for a specific tank variant might exist in a depot hundreds of kilometers away, while the vehicle sat immobilized, awaiting a single, crucial component. Supply officers were forced to track not just tank types, but also specific production batches and manufacturing dates when requesting replacement parts. The third surprise focused on the remarkable ease of field repair. American designers had pragmatically anticipated that tanks would inevitably break down under the severe stresses of combat operations, and that necessary repairs would frequently need to occur close to the front lines, rather than solely within secure rear area workshops. They engineered the Sherman so that major components could be removed and replaced by ordinary soldiers using only basic tools. The transmission and final drive assembly, for instance, were bolted to the front hull in a configuration that allowed the entire unit to be extracted simply by unbolting it from the exterior of the vehicle. A field maintenance crew could remove a damaged transmission, install a replacement, and return the tank to operational service within a matter of hours. No specialized cranes were required, nor any equipment beyond standard military-issue tools. This crucial work could be accomplished in a farmyard or a forest clearing, often with the front lines just over the nearest ridge. The Panther's transmission, by stark contrast, was deeply embedded within the hull, accessible only from inside the vehicle through cramped, narrow passages that made any work difficult and painstakingly slow. Replacing it necessitated the removal of the turret, extraction of the engine, and then working in severely confined spaces to disconnect and finally remove the transmission components. This intricate process demanded specialized equipment, highly trained mechanics, and dedicated workshop facilities that existed only in distant rear areas. A Panther that threw a track or stripped a gear in the field might remain out of action for days or even weeks, waiting for recovery and comprehensive repair. The Tiger's complexity presented an even worse scenario. Its intricate design often rendered field repairs impossible. Damaged Tiger vehicles had to be towed back to major maintenance facilities, a task assuming recovery vehicles powerful enough to move a 57-ton tank were even available. Standard German recovery vehicles were simply incapable of handling the immense weight of the Tiger. Special Birch Panther recovery tanks were subsequently developed, but these too frequently suffered from their own mechanical problems. Many Tigers were ultimately lost, not due to enemy fire, but to mechanical breakdowns that could not be rectified before advancing enemy forces inevitably overran their positions. This stark divergence in maintenance philosophy profoundly shaped the entire conduct of armored warfare. American units pushed forward aggressively, confident that damaged tanks could be quickly repaired and returned to action. German units, however, hesitated to advance too far from their established repair facilities, acutely aware that breakdowns in forward areas almost certainly meant the permanent loss of their precious vehicles. The Sherman's inherent reliability was therefore far more than just a mechanical attribute. It became a decisive tactical advantage that influenced every operational decision made by commanders. The German engineers diligently compiled their findings into a comprehensive technical report, meticulously documenting everything they had discovered. They accurately noted the Sherman's vulnerabilities. Its armor was thin by German standards, its main gun was underpowered against modern German tanks, and its high silhouette made it easily spotted and engaged at long ranges. In a hypothetical one-on-one engagement with a Tiger or Panther, the Sherman would almost certainly lose. Yet, buried within the detailed technical specifics was a more troubling observation, one that the report's authors may not have fully appreciated in its entirety. The Sherman was fundamentally simple. The Sherman was inherently reliable. The Sherman could be constructed by factory workers who had never before seen a tank, utilizing standardized parts that originated from manufacturing plants scattered across an entire continent. The Sherman could be transported across an ocean, driven directly off a landing craft onto a beachhead, and maintained by ordinary mechanics working in muddy fields with only basic tools. The German engineers, in their quiet certainty, understood the implications of this. They understood it, and yet they possessed no effective means to counter it. The sheer production numbers themselves told a story that gun caliber and armor thickness simply could not. American factories collectively produced 49,324 Sherman tanks between 1942 and 1945. This immense total originated from 11 different manufacturing facilities, each employing the advanced mass production techniques pioneered within the American automotive industry. The Chrysler-Detroit tank arsenal alone led all producers, contributing nearly 18,000 vehicles. This single facility served as a microcosm of America's industrial mobilization. The site had been agricultural land in 1940. By 1942, it had transformed into the largest tank factory globally, encompassing over 1 million square feet of manufacturing floor space. Workers who had previously built automobiles quickly adapted to tank construction within weeks. The assembly line methodologies perfected by Detroit's automakers translated directly to armored vehicle production. The arsenal operated around the clock, in 3 continuous shifts. Tanks moved steadily down assembly lines, much like cars, with components added at each station until a completed vehicle rolled off the far end. Raw steel entered one side of the factory, and finished Shermans emerged from the other at a rate that would have appeared utterly impossible to German planners, who still conceived of production in terms of highly skilled craftsmen meticulously constructing individual vehicles. This single American facility alone outproduced Germany's entire tank industry during most years of the war. Fisher Tank Arsenal contributed over 11,000 Shermans. Press Steel Car Company built more than 8,000. American Locomotive produced 2,300. Ford Motor Company added nearly 1,700, despite its primary focus on other vital war production. Lima Locomotive Works, Baldwin Locomotive Works, Pacific Car and Foundry, and Federal Machine and Welder rounded out this vast production network. Germany's response was severely constrained by its limited industrial capacity, the increasing impact of strategic bombing, and its own design choices that consistently prioritized bespoke quality over sheer quantity. Total Tiger Eye production from August 1942 through August 1944 amounted to approximately 1,350 vehicles, all originating from the Henschel factory in Kassel. When Allied bombing raids obliterated 95% of the Henschel plant's floor space in September and October 1944, subsequent Tiger II production was catastrophically affected. Fewer than 500 of these formidable heavy vehicles were completed before the war's end. Panther production, distributed across manufacturers like MAN, Daimler-Benz, and MH, totaled roughly 6,000 tanks, despite it being Germany's highest priority armored vehicle program from 1943 onward. The Panzer IV, Germany's most numerous tank and the reliable backbone of its armored forces for much of the war, achieved a production total of approximately 8,500 vehicles from 3 manufacturing facilities. The resulting arithmetic was devastatingly clear. For every single Tiger tank Germany managed to build, America produced 37 Shermans. For every Panther, 8 Shermans rolled off American assembly lines. The Germans could hypothetically win every tactical engagement by a factor of 3 to 1 and still be utterly overwhelmed by the sheer volume of American production. Even at theoretical exchange rates of 5 to 1, which German tankers rarely achieve consistently, the fundamental mathematics overwhelmingly favored the Americans. The significant cost differential further compounded the problem. A Tiger I cost 250,800 Reichsmarks to produce with early production units before manufacturing efficiencies were gained, reaching as high as 800,000 Reichsmarks. A Panther cost 117,100 Reichsmarks. A Panzer IV cost 103,462 Reichsmarks. Even the Sturmgeschütz III, Germany's most economical armored fighting vehicle, still required 82,500 Reichsmarks. German industry expended enormous resources constructing a small number of extraordinarily capable vehicles, while American industry mass-produced merely acceptable vehicles in quantities that defied conventional comprehension. The resources consumed by a single Tiger could have produced multiple Panzer IVs. The resources devoted to one Panther could have yielded multiple Sturmgeschütz assault guns. But German military culture demanded the absolute best, and the best proved to be the enemy of enough. The strategic implications extended far beyond simple production figures. German tank losses were effectively permanent. Every Tiger destroyed represented months of precious factory production that could never be recovered. Every Panther lost in combat or to mechanical failure was an irreplaceable asset, given the severe constraints on German industry. American losses, conversely, were viewed as temporary setbacks. Every Sherman destroyed was replaced by fresh production within weeks. The assembly lines never ceased operation. The transport ships continued their relentless crossings of the Atlantic. The flow of new vehicles was constant and unyielding. This created a profound asymmetry in how the two belligerents could prosecute the war. Germany was compelled to conserve its armor, deploying it cautiously for decisive engagements where success seemed probable. America, however, could afford to employ its armor aggressively, accepting losses that would have crippled German formations, because replacements were perpetually in transit. Albert Speer, who assumed the role of Reich Minister of Armaments in February 1942 and dramatically boosted German war production through rationalization and the ruthless utilization of forced labor, later characterized the conflict as a direct contest between two distinct systems of industrial organization. Germany's approach, which Speer controversially termed overbred, demanded exacting requirements and resulted in small numbers of highly sophisticated, technologically advanced systems. America's approach, by contrast, relied on what Speer described as the art of improvisation, producing vast quantities of equipment that was good enough to achieve the mission, even if it did not represent the pinnacle of performance in any single category. The reliability gap proved more decisive than any theoretical difference in firepower or armor protection. German tanks were undeniably magnificent when they operated as designed. The persistent problem, however, was their frequent failure to operate at all. The Panther made its combat debut at the Battle of Kursk in July 1943, destined to become the largest tank engagement in history. German commanders had rushed the new tank into service despite clear warnings from engineers that production models had not undergone adequate testing. The High Command desperately sought to deploy Panthers at Kursk, hoping to exploit their perceived technical superiority against Soviet armor. They received Panthers at Kursk. What they did not receive were Panthers that could reliably fight. The initial results brutally validated every concern the engineers had raised. Contemporary German reports documented the disaster in chillingly clinical terms. Before reaching the first preparation area, 50% of vehicles were inoperative. Two-thirds of these failures involved engine breakdowns. The remaining third suffered from transmission and steering malfunctions. Panthers were breaking down during the road march to the battlefield, not in direct engagement against Soviet tanks. Within a single week of combat, over 180 Panthers had been reduced to approximately 40 functional tanks. The operational readiness rate hovered barely above 16%. The most technologically advanced tank in the German arsenal could not even traverse the distance to the battlefield without suffering a disabling breakdown. Soviet tankers certainly destroyed some Panthers, but German internal mechanical problems accounted for far more. These persistent issues plagued the Panther throughout the war, despite continuous engineering efforts aimed at addressing them. Panther operational readiness rates in 1944, after more than a year of production refinements, averaged a mere 54% across all fronts. Monthly statistics showed only gradual improvement as manufacturing processes matured. In February, a meager 37% of Panthers were combat ready. This rate slowly climbed to 50% by April, reaching 78% in May, before fluctuating throughout the summer and fall. At no point did Panther operational rates consistently exceed 80%. The Sherman, in stark contrast, achieved operational readiness rates consistently approaching 85% under comparable conditions. American tank crews could depend on their vehicles starting, running, and fighting when ordered into action. This inherent reliability was not an accident. It was the direct consequence of design decisions that prioritized maintainability over maximum performance, stemming from manufacturing processes that emphasize consistent output over individual craftsmanship, and facilitated by a logistics system specifically designed to keep vehicles running rather than waiting for specialized repairs. Soviet evaluations of Lend-Lease Shermans further corroborated American reliability data. The Soviet 6th Guards Tank Army, which operated M4A2 diesel Shermans alongside their indigenous T-34s, determined that their American tanks had a service life of 2,000 to 2,500 kilometers, a figure comparable to their own vehicles. Engines typically required inspection at approximately 100 operating hours and could function for 250 to 300 hours before necessitating major maintenance. Soviet crews genuinely appreciated the Sherman's reliability, even as they noted its undeniable vulnerability to German guns. The severe consequences of unreliability multiplied throughout German armored formations as the war relentlessly continued and maintenance resources grew increasingly scarce. A meeting of the Panzer Commission on January 23, 1945, documented the full scope of the unfolding crisis in terms that starkly revealed the desperate nature of the situation. The assembled officers reported 370 defective Panther final drives awaiting repair or replacement. They noted 500 defective Panzer IV final drives that had failed before the anticipated Eastern Offensive could even commence. They also reported roughly 100 Tiger failures of various mechanical types. These are not vehicles destroyed by enemy fire. These were vehicles abandoned because their own internal components had catastrophically failed. General Tom, a participant in the meeting, stated bluntly that an orderly utilization of tanks was simply impossible under these conditions. He observed that the troops, referring to the tank crews, lose their confidence and in some situations abandon the whole vehicle just because of this problem. German tank crews, whose primary duty was to engage the enemy, found themselves instead battling the inherent flaws of their own equipment. Crews who should have possessed unwavering confidence in their machines instead learned to anticipate breakdowns and plan their movements accordingly. The psychological toll of unreliability compounded its practical impact. The 101st SS Heavy Panzer Battalion provided a grim illustration of this problem in microcosm. When alerted for deployment to Normandy on June 7, 1944, merely one day after the Allied D-Day invasion, the battalion theoretically possessed 45 Tiger tanks, with 37 officially listed as operational. The road march from their assembly area near Beauvais to the combat zone around Villers-Bocage should have been a routine movement, approximately 165 kilometers over established French roads. Instead, a combination of catastrophic mechanical breakdowns and relentless Allied fighter-bomber attacks reduced their available fighting force to approximately 6 operational vehicles by the time they reached the battle area on June 13th. Tigers broke down repeatedly along the route. Recovery vehicles struggled immensely to tow the massive tanks. Air attacks destroyed or severely damaged vehicles that had stopped for necessary repairs. An entire heavy tank battalion had been reduced to a handful of operational vehicles before firing a single shot at the enemy. Michael Wittmann's now famous action at Villers-Bocage on June 13th certainly demonstrated what a skilled crew in a powerful tank could achieve. In a matter of minutes, Wittmann's single Tiger destroyed more than a dozen British vehicles, including other tanks, armored cars, and troop carriers. This action became legendary, cited for decades as irrefutable proof of German armored superiority. But the broader context revealed the stark limitations of German doctrine. The 101st SS Heavy Panzer Battalion had 45 Tigers on paper. It had 6 in actual combat. The remaining 39 were either broken down, destroyed by air attack, or still struggling toward the front lines. Wittmann's individual brilliance could not compensate for systemic failures that rendered the majority of his battalion's combat power uselessly immobilized along French roads. The Battle of Ericourt in September 1944 offered the most comprehensive test of Sherman versus Panther in sustained combat. This engagement, fought in the Lorraine region of France, escalated into the largest American tank battle on the Western Front until the Battle of the Bulge 3 months later. The German 5th Panzer Army committed 262 tanks and assault guns to a counterattack, specifically aimed at halting General Patton's advancing Third Army. This force included 107 Panthers, 75 Panzer IVs, and 80 assault guns, substantial numbers by late war standards. Opposing them was Combat Command A of the American 4th Armored Division, equipped primarily with M4 Shermans and M18 Hellcat tank destroyers. The German forces suffered from crippling disadvantages that bore no relation to their equipment's theoretical specifications. The 111th and 113th Panzer Brigades had been formed only weeks before being committed to battle. The 113th, for instance, was organized on September 4th, 1944, a mere 15 days before being thrust into action. Crews had received drastically shortened training schedules and demonstrated minimal proficiency in tactical maneuvering. Many had never operated as cohesive units before. Some Panthers were still receiving final adjustments from factory representatives when the urgent attack orders arrived. The 5th Panzer Army completely lacked integral reconnaissance units and was thus forced to advance blindly into established American positions. German commanders had no intelligence on the Americans' precise location, their strength, or their deployment. They attacked expecting to encounter disorganized rear area units and instead collided with experienced armored formations that had been fighting continuously since the Normandy landings. American tactics skillfully exploited every German weakness. Shermans utilized their faster turret traverse mechanisms to engage targets more quickly than Panthers could respond. The Sherman's turret could complete a full 360-degree rotation in 15 seconds. The Panther required more than double that time for the same movement. In close-quarters combat, where fractions of seconds often dictated who fired first, this difference proved decisive. American crews also fought from well-concealed defensive positions, effectively negating the German advantage in long-range gunnery. Panthers and Tigers excelled at destroying enemy tanks at distances of 1,000 meters or more. But the rolling terrain around Ericourt offered few such extensive sight lines. Combat frequently occurred at ranges of 300 to 500 meters, where the Sherman's gun could reliably penetrate Panther side armor, and where faster reaction times mattered far more than superior optical systems. Morning fog on several days allowed American tanks to close to ranges where even frontal engagements sometimes favored the faster-firing Sherman. German crews, accustomed to engaging at long range, suddenly found American tanks emerging from the mist at point-blank distances. Their specialized training and experience failed them. Faster American reactions succeeded. On September 19th, American Shermans skillfully flanked and destroyed 11 panzers, employing the dense fog as perfect concealment. Captain Lamesson's C Company of the 37th Tank Battalion arrived at a defensive position on a ridgeline just 3 minutes before 8 Panthers appeared from mist. Those crucial 3 minutes made all the difference. Lamesson's tanks were already positioned and fully prepared. The German tanks were advancing blindly. Lamesson's crews engaged immediately, knocking out 4 Panthers before the German crews could effectively identify targets and return fire. The Americans then withdrew over the ridge, repositioned several hundred meters to the south, and reappeared to engage the surviving Panthers from a completely new angle. The remaining German tanks, already disoriented by the loss of half their number, were systematically destroyed. The battle raged for 11 days as German forces launched repeated attempts to breach American positions. Each subsequent attack followed a depressingly similar pattern. German tanks advanced without adequate reconnaissance. American forces detected their movements and prepared devastating ambush positions. Combat invariably occurred at ranges that negated Germany's technical advantages. German losses steadily mounted. When the engagement finally concluded on September 29th, German forces had suffered 86 tanks confirmed destroyed and 114 damaged or broken down. Only 62 of their original 262 vehicles remained operational. American losses, by contrast, totaled 25 tanks and 7 tank destroyers, a mere fraction of the German casualties. The aftermath of the battle proved as revealing as the fighting itself. American maintenance crews swiftly recovered damaged Shermans from the battlefield, returning many to active service within days. German recovery efforts salvaged some vehicles, but they critically lacked the necessary spare parts and workshop capacity to repair them quickly. The American force that had fought at Ericourt was restored to full strength within 2 weeks. The German force that had initiated the attack never recovered. The lessons were starkly clear to anyone willing to acknowledge them. Superior equipment meant nothing if it could not be kept operational. Tactical advantages were meaningless if units could not generate sufficient combat power to exploit them. The most powerful tank in the world was utterly worthless if it sat immobilized in a repair depot while the enemy advanced. Military historians have frequently cited Ericourt as compelling evidence that crew quality and tactical training can be far more crucial determinants in the outcome of a tank battle than the purely technical merits of the tanks themselves. The Panther was demonstrably superior to the Sherman by every metric German engineers valued, but paper specifications did not fight at Ericourt. Under-equipped, under-trained crews in mechanically unreliable vehicles fought against experienced American tankers who thoroughly understood their equipment and instinctively knew how to exploit its advantages. German officers who survived the war often provided assessments that directly contradicted the pervasive mythology of German tank superiority. General Otto von Manteuffel, who commanded the 5th Panzer Army during the Ardennes Offensive and was widely regarded as one of Germany's most respected armored warfare experts, provided extensive interviews to British military historian B.H. Liddell Hart after the conflict. Manteuffel emphasized that Much more importance should be placed on the speed of the tank on the battlefield than was generally believed before and during the war. The ability to move rapidly, to reposition faster than the enemy could react, to concentrate force at decisive points. These factors mattered as much as raw firepower and armor protection. Maneuverability, Manchefel unequivocally declared, develops into a weapon and often ranks equal to firepower and armor protection. This principle was precisely what American designers had embraced and German designers had largely rejected. The Sherman prioritized mobility and consistent reliability over achieving maximum individual combat power. It could reach locations German tanks could not, remain operational when German tanks broke down, and concentrate its strength faster than German formations could effectively respond. The Tiger and Panther, conversely, prioritized firepower and protection, optimizing for the decisive engagement while neglecting the countless other factors that determined whether tanks even reached the battlefield ready to fight. Albert Speer himself acknowledged the Sherman's unexpected capabilities in his post-war memoir, Inside the Third Reich. Describing reports from the Italian front, where American armor operated in challenging mountainous terrain that should have favored defenders, Speer wrote candidly about what German commanders were observing. The Sherman climbs mountains our tank experts consider inaccessible to tanks, Speer recorded. One great advantage is that the Sherman has a very powerful motor in proportion to its weight. Its cross-country mobility on level ground is, as the 26th Panzer Division reports, definitely superior to that of our tanks. This was a remarkable admission from the very individual responsible for German war production. German tank experts had designed vehicles meticulously optimized for destroying enemy armor in direct combat. They had not designed vehicles capable of keeping pace with Shermans across the varied, demanding terrain of a continental war. American tanks ventured where German tanks could not follow. American tanks arrived at battles German tanks never reached. The deeply ingrained institutional cultures that produced these divergent approaches proved as crucial as the tanks themselves. American military doctrine emphasized adaptability and a continuous process of improvement. After-action reports from combat units flowed rapidly back to training establishments and design bureaus within weeks. Problems identified in the field were swiftly analyzed by engineers, who then revised specifications and modified production procedures. The Sherman that rolled off assembly lines in 1944 incorporated hundreds of refinements based directly on combat experience gained in North Africa, Sicily, and Italy. German military culture, by contrast, had ossified around rigid doctrines and entrenched personal loyalties that actively discouraged honest assessment of problems. Initiative in questioning established approaches was suppressed. Failure to achieve assigned objectives often proved fatal to careers. Engineers who identified fundamental design problems with the Panther transmission were frequently told to find solutions, not to challenge design decisions that had been approved by senior officials and endorsed at the highest levels of the Reich. Hitler himself exacerbated this rigidity through constant, often intuitive interference in weapons development. He demanded changes to tank designs based on personal instinct rather than sound engineering analysis. He insisted on heavier armor and larger guns, even when his own engineers warned that existing automotive components simply could not support the additional weight. Commanders quickly learned that disagreeing with decisions that had reached the Führer was career-ending at best and potentially fatal at worst. The honest assessments that might have corrected German tank design were thus stifled, replaced by reports that instead told the leadership precisely what it wished to hear. Problems were minimized. Failures were attributed to external factors beyond control. The systematic analysis of what was going wrong and why, a hallmark of American military institutions, became a dangerous endeavor in a system where acknowledging problems could be misinterpreted as defeatism. The American system, in contrast, often appeared chaotic. Different units frequently developed different solutions to similar problems. Coordination between various branches of service was imperfect at best. Arguments about doctrine and equipment continued throughout the war. But this apparent chaos proved productive. Ideas that proved effective survived, propagating rapidly throughout the fighting force. Ideas that failed were simply abandoned, irrespective of whose reputation might be attached to them. The organization as a whole became demonstrably more effective, even when individual components struggled. By the spring of 1945, the profound consequences of these fundamentally different approaches had become undeniable. American armored divisions advanced across Germany with operational readiness rates that German commanders could only gaze at with envy. Sherman tanks that broke down were rapidly repaired and returned to action within days. Spare parts flowed ceaselessly forward through a logistics system that continued to function despite the inherent chaos of mobile warfare. Replacement vehicles arrived steadily from ports where transport ships delivered a continuous stream of new production. German tank formations, meanwhile, had disintegrated under the crushing weight of their own complexity. Vehicles that should have been fighting instead sat idle in repair depots, indefinitely waiting for parts that would never arrive. Crews abandoned Panthers and Tigers, not due to enemy fire, but because transmissions failed, engines seized, or final drive stripped. The magnificent machines, once intended to reverse the tide of the war, now rusted in fields and forests across the Reich, silent monuments to a design philosophy that had fundamentally prioritized the wrong objectives. The men who had dismissed American industrial capacity as mere propaganda now watched American factories bury them under an avalanche of steel. The engineers who had scorned the Sherman as crude and underpowered witnessed their own sophisticated designs fail repeatedly, while the simple American tanks relentlessly kept running. The generals who had staked everything on quality, triumphing over quantity, learned, too late, that quantity possessed a devastating quality all its own. The Sherman was never considered the best tank of World War II by conventional technical measures. Its main gun was merely adequate rather than truly exceptional. Its armor offered protection against some threats, but remained vulnerable to others. Its silhouette was higher than ideal for a combat vehicle. In a controlled, direct test against a Tiger or Panther, with both vehicles at peak operational capacity and crews of equal skill, the Sherman would most likely have lost. But wars are not controlled experiments. Wars are fought across continents and oceans by millions of individuals over years of sustained, brutal effort. Wars are ultimately won by nations capable of constructing weapons faster than they lose them, shipping them to the front lines faster than they are destroyed, keeping them operational through mechanical failures and combat damage, and replacing crews faster than casualties deplete them. By these decisive measures, the measures that truly determined victory, the Sherman was arguably the single most effective tank of the entire conflict. The German engineers at Kummersdorf, in their quiet professionalism, understood this reality, even if they could not explicitly state it in their official reports. Their technical documents accurately and in detail noted the Sherman's inherent weaknesses. But between the lines, within the meticulous descriptions of standardized parts, field maintainability, and simple, robust design, they documented something far more unsettling. They had observed an entirely different approach to warfare, one that German industry was utterly incapable of matching and German doctrine proved unable to counter. The very tank they had disassembled that. Summer had survived over 5,000 miles of combat operations. It had traversed an ocean on a transport ship, rolled off a landing craft onto a North African beach, fought through treacherous mountain passes and arid desert valleys, and arrived at their proving grounds still fully operational. Their own Panthers struggled merely to complete a road march without suffering disabling breakdowns. Their Tigers frequently required specialized recovery vehicles and extensive workshop facilities for even routine maintenance. The German engineers duly filed their report and returned to their ongoing work, designing even more sophisticated vehicles with more powerful guns and thicker armor. They continued to hold the belief that sheer technical superiority would, in the final analysis, prevail. They clung to this conviction, even as American factories produced another Sherman every few minutes, even as their own Panthers sat immobilized awaiting critical spare parts that never arrived, and even as the tide of the war turned irrevocably against them. The fundamental misjudgment of the Sherman by German engineers was not merely a failure of intelligence or detailed analysis. It represented a profound failure of imagination. German engineers looked at the American tank and saw only what their existing framework allowed them to see: a crude, unsophisticated machine ill-suited for modern armored warfare. They failed to perceive what truly existed: a weapons system purpose-built for industrial conflict, forged by a nation that grasped the critical importance of production and logistics as strategic factors entirely equal in weight to firepower and armor. This was the singular aspect about the captured Shermans that German engineers found themselves simply unable to reconcile. They could not conceive that a nation would deliberately construct a tank that was good enough rather than striving for the best possible by their own metrics. They could not accept that reliability and maintainability could matter more than maximum individual combat performance. They could not believe that a simple approach would ultimately defeat their sophisticated one. Their entire engineering culture, indeed their very national identity, had taught them that true excellence equated to complexity, and that complexity invariably signified superiority. They were wrong in every single respect. The vast factories that once constructed Sherman tanks have largely been repurposed for other endeavors or have been entirely demolished. The workers who once staffed them, the welders, the machinists, the assemblers who forged a tank every few minutes, around the clock, have since passed into history. The immense war they helped bring to an end concluded 8 decades ago. The Sherman tank now resides in museums across the globe. It stands as a relic from a conflict that reshaped the 20th century, smaller than many visitors anticipate, simpler than they might imagine. They do not perceive what those German engineers saw when they meticulously examined their captured specimen at Kummersdorf. They do not see the factories that could produce one every few minutes, operating 3 shifts a day, 7 days a week. They do not see the elaborate supply chains that could deliver spare parts across oceans and continents to wherever they were most desperately needed. They do not see the diligent maintenance crews that could return damaged vehicles to action in mere hours, utilizing standardized parts and readily available basic tools. They do not see the robust training programs that could transform ordinary civilians into competent tank crews in a matter of weeks. They do not see the underlying system, and it was this system, far more than the tank itself, that ultimately won the war.